Hello, my name is Steve, and I've been thinking about how should we build robots so that designing or learning the controller is easier. This is something I think most of us are familiar with. There are some robots that require a lot of fine-tuning before the controller works. And then there are other robots, like the toddler here on the right, where almost any set of parameters that we try will give some reasonable behavior. And it turns out that in these cases, it's usually also a lot easier to find good parameters. This is very closely related to robustness, and the question we're really answering is, how do we quantify the robustness of a system's natural dynamics before we've designed the controller? We're going to answer this with something called viability theory, so let's start there. In viability theory, we don't start by defining the behavior that we want, but instead by defining failure sets. These are all the states that we absolutely want to avoid. Next, we define the viability kernel. This is the set of all states from which there exist actions that keep us inside the set. So in other words, if we're in the viability kernel, we can choose actions that will move us to other portions of it. We can also leave the viability kernel, but once we're outside, we can never get back in. And within finite time, we will end in the failure set. When we're designing the control policy, what we're trying to do is generate a region of attraction that converges back to some desired behavior. Naturally, we would want this region of attraction to be as large as possible, but by definition, the region of attraction has to be a subset of the viability kernel. So now, when we design the system, we want to do one of two things. We either want to make the viability kernel as large as possible. This would mean that it's possible to generate a larger region of attraction. But what I'm going to argue is more important is we want to put some structure in the dynamics that makes everything more robust. And this robustness is what's going to make it easier to find controllers. Now it turns out that to find this structure, we need to look at viability not just in the state space, but in state action space. So let me illustrate this with this very simple toy example. Imagine you have a spaceship that lives in a one-dimensional world with just 5 states, which we're going to label 1, 2, 3, 4, 5. State 5 is our failure set. You can imagine this as crashing into the ground. These arrows on the left represent the natural dynamics of the system, and we also have some control inputs, some actions, which are do nothing, apply a thruster, or apply 2 thrusters. This gives us our state action space and also our transition map, so our system's dynamics. And this is just telling us that if we're at state 1 and we do nothing, we will end up in state 2, etc. Now for this simple system, it's trivial to find the viability kernel just by inspection. And these are states 1, 2, and 3. State 4 is not viable because no matter which action we choose, we will end up in the failure set within finite time. Now so far, this has been standard viability theory. The first step that we took is to extend this into state action space and obtain our viable set QV. This is the set of all state action pairs that map through the dynamics back into the viability kernel. And we have an important connection between these two objects. The viability kernel is always the projection of the viable set back into state space. And this connection gives us forward positive invariance. The reason this viable set is useful is that if we have a set, we can put a measure over it and measure the n-dimensional volume of this set. More specifically, we're going to define a state-dependent measure. And what we're going to do is pin the state and then look at that slice of the state action space. And we're going to measure the volume of the set of viability-maintaining actions that are available to us from that state. What this means is, if we have a very large measure, we're very robust, and it's very easy to find an action that will keep us viable. But if the measure is very low, like in state 3, then our control policy has to be very precise and very deliberate, because any small uncertainty could make us fail. Now let's look at these same objects, but for a more interesting example. This is the spring-loaded inverted pendulum. It's a model that's commonly used to describe running. I won't go into the details of the dynamics here, but you can find all of this in the paper. The important part is we use a representation that gives us discrete time dynamics with a continuous two-dimensional state action space. So just like before, our state space is on the vertical axis, and the action space is on the horizontal axis. We have here our viable set QV, and its projection into state space, the viability kernel. Now, any control policy that we might be interested in must live in the viable set. And this is what we're saying here. A policy is a viable policy if for every state in the viability kernel, that policy maps the state back to an action such that the state-action pair is in the viable set, and therefore transitions through the dynamics back into the viability kernel. Now, this is a very general condition. The only requirement we've placed on the control policies is that they should never fail. But we haven't defined the control objective, and we haven't even decided on the parameterization. So we could have a linear control policy, like here. We could have something more sophisticated. Or we could even have something stochastic, where the policy randomly samples an action from inside the viable set, in which case we would never converge to anything, but we would also never fail. And the state would just bounce around the viability kernel haphazardly. Because this is general to all viable policies, we can now compare different designs, different robots that we want to build, by comparing their viable sets. For example, here we compare another slip model with a nonlinear spring. And here is the viable set that we obtain. Now, if we look at the projection into state space, the viability kernel is exactly the same as before. So if we only look at things in state space, we wouldn't see a difference. However, in state action space, it is clear that the viable set has a much larger measure. And this measure is what's going to give us robustness. In particular, we're interested in robustness to noisy actions, because this is how we introduce exploration to our learning algorithms. We will typically inject additive noise over our policy. The effect is that our policy now has to live in a more conservative subset to ensure that we maintain positive forward invariance despite the noise that could otherwise potentially push the action out of the viable set. As we add more noise, these conservative subsets will continue to shrink until they become empty sets. At this point, no controller exists that can avoid failure. This means that if we design our robots to have large viable sets, like the example on the right, then we can explore much more aggressively on that robot. We show an example in the paper where we maximize the viable set of a simple one-legged robot using a black box optimization scheme. However, so far we've relied on brute force to compute the viable set. The saving grace is that since we're in the design phase, we can do this offline, and this computation can be trivially parallelized. So you can still push the dimensionality to some extent by putting it on a cluster and letting it run over the weekend. But to make this practical, we do need computationally efficient methods to compute or approximate these invariant sets. We also think there's a lot of promise to use these mathematical objects directly for control. And we have an extension where we formalize safe model-free learning. And if you're interested in this, I'd be happy to chat with you about this as well. Finally, I'd like to point out that we've made our code available online, and we'd be happy to help you try it out.